Yeah, good morning, good afternoon, everyone. In the next 30 to 40 minutes, I'll be talking about the topic key priorities for powering wearables. I'll start with the introduction where I'll talk about the various market trends in the wearable space. And then basically I'll also highlight what are the challenges in the wearable design when you're designing a wearable product with primary focus on power management. And what we'll do is we'll zoom into two of the use cases. One is, let's say, the smart sports watch and the fitness bands, and the other one is connected medical patches, followed by conclusion. In all my slides, I have focused more on what is currently going on in the industry, what in my experience, my customers and also companies focus on, the parameters they focus on while designing a wearable product for their end users. And I hope that after this session, you can also have a similar mindset when you guys will be designing your product, hopefully in the future with a similar mindset of having an end product which end users can use. So let's start off with the wearable market analysis. So I find this graph from IDC. These guys are quite good in predicting market report in this wearable space. So this graph is quite nice, which is predicting the trend that the wearable products are growing over the year. But also it highlights the various wearable products seen here. So let's look at some of them. Let's start with the wristband. The wristband, what it states, which is some of the products are stated here, what it states that it is quite high volumes currently, but as you can see, there's not much growth. The volumes over the years in the coming years will be quite flat. And the ASP basically, which is the cost of the device, will be going down. So there'll be a lot of focus put forth by the companies to design the product in a very low cost and efficient way. On the other hand, if you look at the watches, currently I think the bulk of the volumes that the watches that are being shipped this year are dominated by Apple's Apple Watch and Samsung. But over the years, you will see that this market segment is also growing quite a bit. And let's say other watches, not necessarily the smart watches, but also watches with high resolution displays, getting very popular already now. And I think this trend will continue over the years. The other kind of wearable product, the TWS, the True Wireless Stereo Earbuds, I think this has been around for over the last 4 or 5 years, and this is an extremely popular product these days, and the trend is expected that it will continue to grow over the years as well. There's also a segment in the consumer space. So this graph is primarily focusing on the consumer space. In the consumer space, you also have other kind of wearables like footwear, clothing, or smart ring. These, you see that every now and then these products come in the market, but as you can see, and is correctly indicated, the volumes and the success rate of these products are not very high. So primarily in the consumer space, I would say the bands, the watches, and the TWS earbuds are quite popular. On the other side, the wearables can also be associated with medical space as well. In the medical space, I have focused mainly on, let's say, the connected medical patches, and you see that these are getting more and more interesting, and over the years there'll be quite some volumes that will be shipped in different parts of the world. Even when we interact with many of our customers, we see that it's getting very popular, and we are talking with them to make it even smarter by adding connectivity to their devices. So some of the products in this space is, let's say, temperature sensor patch. I think this has also become very popular. because of the COVID scenario that we are facing, unfortunately, these days. But also things like constant glucose sensor patches for constant glucose monitoring, so which is shown here on the top left, but also things like monitoring the heart rate, ECG, or let's say the oxygen saturation level in your blood with the SpO2 sensors. So all these kinds of medical patches are getting quite popular and will be used more and more for tracking the patient's health data over the years. So this was a bit about the market. So talking about what are the key priorities in wearable designs. So personally, I could think of these six aspects that primarily we focus on. So there is security. I think be it a smartwatch or a patch, these are quite personal devices which share, which basically saves user data. And also, I think many of the smartwatches are also used for payments. So security is a very important aspect when it comes to wearable design. Same with connectivity. In connectivity, actually, most of devices interact with the smartphone using Bluetooth Low Energy. And I think for data exchange, this is used, I think, across all products when it comes to connectivity. And when it comes to audio, the Bluetooth Classic flavor of the Bluetooth is used, and in some products Wi-Fi is also used when you have to, let's say, download music and other use cases similar to that. The other aspect is also audio and voice. I think if you look at some of the watches these days, it supports functionality like voice call, streaming music without connecting to the smartphone, let's say when the user is going out for a run. And also things like hot word detection. So let's say if you, without the phone, if you want to switch on a light, set a timer or something similar of that sort, then these kind of functionalities in the audio and voice space is also supported by the wearable devices these days. Display and graphics, I think this is a very important aspect these days, especially in the watches and the band segment, not necessarily too much associated with the patches and the TWS space. But in the watches, based on my experience, when I interact with any of my customers, the primary discussion is about how you can support such a big resolution display with the given frame rate. So it's a very hot topic these days, and there has been a lot of focus when it comes to watches and bands. Sensors and processing. I think over the years, if you see, the watch was the bands was typically having notifications apart from time, and maybe heart rate monitoring was there. But I think if you look at the current bands and the watches, things like ECG monitoring, but also things like oxygen saturation monitoring with the SpO2 sensor, and the processing around it is also quite an important aspect in the wearable space. Lastly, which is also the topic of my presentation, is power and battery management. So let's look at some of the lifetime of the products that I have here. With the smart watches, the bands basically have a lifetime of multiple weeks before you need to charge again. Watch is typically less than, I think, around 5-6 days, and smart watches are a couple of days, 1 to 2 days. For the true wireless stereo, it is even more important because you have, let's say, 5 to 8 hours of streaming music or audio in one charge. And for the patches, I see patches are more like a disposable kind of devices. So you have the user use it once, and depending on the lifetime of the product, be it days or weeks, you just dispose it after that. So you see here, all these products are getting popular, but it is just one more device that the user has to charge. So battery life is very critical for wearable adoption because of this reason. And in the upcoming slides, we'll focus primarily on power management and battery management. Instead of going into, let's say, all those products, what I have done is I have selected two products. So as a use case, so I'll start off with discussing a lot about bands and watches. And these products are powered by lithium ion, or let's say lithium polymer type of batteries whose output voltage is typically 4.2 to 4.35 volts, and the capacity is typically less than 500 milliamp hours. So around 400 milliamp hours is popular more in the watches segment. And if you consider the band segment, then the battery capacity is somewhere around, let's say, 100 to 200 milliamp hours. On the other end of the spectrum, the connected patches is a different ball game altogether. They are powered by batteries which are quite exotic. So let's say small silver oxide batteries, or even these days, because of the form factor nature of the patches, we have printed batteries which you can just, along with your electronic product, can stick in your skin. So these batteries are quite exotic. It enables the use cases in a very nice way, but also it brings immense amount of design challenge. So be it the output voltage that you need to support, which is lower than 1.8 volts, or the capacity, which is quite small, especially if you look at the printed batteries, they are even in the micro, let's say they are, let's say 500 to microamp hour to 1 milliamp hour per cell. So you see that the capacity of these batteries are quite less, and you need to design your system in such a way that you can support your product for multiple days, weeks with such low capacity batteries. So let's start with focusing on watches and the bands. So what I have done is there's a lot of things attached, but this is a very nice use case system diagram of a band or a watch. In the heart of a system, you typically have a microcontroller, a sensor node controller, even a main application processor, which can be the main core of the MCU. And then, as I mentioned, you have BLE connectivity for data exchange. So depending on the product, these three aspects can either be implemented by, let's say, one single chip solution, which is quite popular to drive cost in the band segment. But let's say if you go towards more complex products like watches, then you basically have a separate solution for sensing and sensing. You have dedicated application processors doing the number crunching. And then typically, I think for the BLE, the Wi-Fi and even the Bluetooth is combined in the combo chip, and it's a separate chip altogether. Apart from the heart of the system, in the yellow orange space, you see that there's a bunch of memories associated with any wearable product. So you have flashes where you typically store the application firmware, but also you have multimedia card which are embedded multimedia card where you store things like music, or you can have a secondary flash as well where you store all sorts of static graphic. And in most of the cases, specifically if you are targeting high resolution displays, then internal memory of the MCU system is not sufficient, and you typically have to have an external RAM, external memory, where you store the frame buffers of the graphics. So this is about the storage and the memories. More interestingly, in the green, you have mostly about sensors. So be it a heart rate sensor or an accelerometer or a gyro sensor, be it SpO2. So all these sensors also needs to be powered and communicate with the main MCU or the sensor hub. as the case may be. But also you have things like haptics, you have NFC for payment, you have Wi-Fi, as I mentioned, for downloading music, you have GPS for navigation, and also on the left bottom here you have let's say typically you have connected a mic but also speaker to enable use cases like voice call, but also keyword detection, as I explained. And on the top left you have the displays, which are typically either LCD, and the OLED technologies are more popular these days on the display side. And display communication and power management of the displays are a quite deep and interesting topic, and the power management aspect of it I'll cover in the upcoming slides. So this in short basically incorporates all kind of elements that are in a band or a watch use case. I think the other thing which I missed was you typically have a USB charger powering your battery, the lithium ion or lithium polymer battery as well. So let's look at what are the key design challenges and what does it mean for the users. Starting with battery charging. So battery charging is a important design aspect that customers look into with great detail, especially because it also involves a lot of safety risk. But from a user point of view, they are interested in how fast they can charge the product. So we'll see how we basically design the charging element so that we can have this user experience as nice as possible, which is faster charge time. The other design challenge is powering the different components efficiently and with a low BOM, so low bill of materials. So I'll also show that I showed the different elements that are making up the product, but also I'll show what are the different voltages associated with those components, be it sensors, be it haptics, be it displays. And you have to have power management ICs or blocks that can power those components in a low cost and an efficient way, so that it results in longer product lifetime for a user, and it results in lower cost for the devices, so that it can be adopted in volumes. The last two design challenges that I could think of was low power sensing and processing and low power connectivity for data transfer. And I'll focus a lot on that. And for the user, this again means longer product lifetime and longer duration before he needs to charge his product again. So let's look at battery charging. Again, the problem statement here is to charge the battery as fast as possible. Before I go into the solution, I would like to explain, I'm not sure if all of you are aware, but lithium ion or these kind of batteries are typically charged in a constant current and a constant voltage kind of fashion. Before the constant current, if the battery is completely depleted, then you also have a pre-charge phase, but I'll not focus on that. So in the first phase, you see that the current going into the battery is constant, and the cell voltage typically rises in this space, which is denoted here in purple, and the current, which is denoted here in yellow, is constant. And in the second phase, which is the constant voltage, the cell voltage will be constant, and the charger ASIC will basically try to adapt the current in such a way that the cell voltage is constant. So you see here that the current starts decreasing because you are also reaching the capacity of the battery. So the current starts basically decreasing. So what I infer from this graph is you see that in the constant current phase, bulk of the capacity is already reached. So it's a very important phase when it comes to how fast you can charge the battery. So bigger the constant current or bigger the current, that you can put into the battery, the faster you can reach a minimum capacity which will enable the user to use the product for a longer time. But it has again its challenges because there's a lot of chemistry involved in the battery, so you cannot put any amount of current. So you have to find a right balance between the amount of current that you can put into the battery and the amount of time that it will take to charge the battery. But typically the what customers typically use based on the spec of the batteries is 1C. So let's say if the capacity of the battery is 300 milliamp hours, then typically in the constant current phase, customers are charging the battery with 300 milliamp hours. And in some cases, if you are fast charging it, then you are then you can go a bit beyond, but also it affects the chemistry in a different way, and then the number of times you can charge and discharge the batteries deteriorates. So there's a lot of considerations you have to take into account. Also, if you are charging from a USB, then it's perfectly okay. Then you can draw as much current as you want. But let's say, as shown in the bottom left over here, if your product uses wireless charging, then also you need to say how much energy and current you can harvest or you can take from the wireless charger, and that can also limit this current capabilities and thus the charge time as well. Another thing that you should take or customers take into account is when you charge your battery with a very large current, then also quite a lot of heat is dissipated and the battery also gets hot. So there's a lot of mechanism in place to sense the temperature of the battery and basically stop charging when the temperature of the battery is beyond the limits as specified by the vendor of the battery. So charging in general is a complex problem, but specifically from a user point of view, you would like to charge it as fast as possible, specifically in this phase, so that in a very short amount of time, the user can have the maximum capacity to use their product for a longer time before he or she needs to charge it again. Let's look at the powering of the different components. So I've shown this use case diagram before, but what I have added here is the different voltages that you need to power the different components. So you typically need around 3 volt or 1.8 volt to power the memories. And I think that is also typically true for most of the sensors. When it comes to heart rate sensors, specifically if I talk about it, you also need higher voltages, especially for the green LEDs that is used to sense the heart rate or the pulse. So this is a challenging part because you need a higher voltage over here. But also when it comes to, let's say, more latest GPS chips or other kind of chips which are now made in lower tech nodes like 22 nanometers or even lower, then you see that much of the system is supplied by even lower voltage like 0.7 volts. So you see that there are multiple voltages that you need to take into account. And then it poses big challenge when you have to design a power management that can output these voltages. So let's see in the upcoming slides how you can power these components, focusing first on the display and then on the rest of the components. The display, as I mentioned, two popular flavors of it is the LCD type or the OLED type. In the OLED type, you see that these are basically have built-in LEDs. But the challenging aspect here is that you need to support quite some voltages. So you have compared to the battery, which is typically from 3 volts to 4.35 volts, you see that you have to boost the voltage to power one of the rails. But also you have a negative rail, which is typically implemented by a charge pump. That also you have to output. And then you have some digital and analog power supply, which is around 1.8 and 3 volts. So there are four voltages that you need to support along with the current requirements to power an OLED screen. So typically what I have seen in this space is like there are dedicated power management ICs powering these displays, especially the OLED ones. And it is, let's say, agreed, or it's an industry norm that you don't expect that the main power management unit will be powering this OLED display. On the other hand, the LCD is a bit different. How you power the LCD is it typically has a backlight, which is a series of LEDs which are arranged in series, and then you can have multiple of them in parallel. So as you see over here is like, since you stack a bunch of LEDs or diodes here, then you typically have to power these diodes in order for it to be on. So if you stack all the thresholds of these diodes, the V out again becomes quite high compared to the output of the battery. So you see here is like you typically need a booster to power the backlight of the display. And then also you have a LED pin which has a current source, because you also need to sync all these currents going through the LEDs into your chip. So these are the things which you need to design while powering the backlight of the LCD. Moving on to the next topic, in order to power the sensors, memories, connectivity, audio, all the different other components, you need to power it in an efficient way. So as I explained you, you have, let's say, 0.7 volts. You have to supply 1.8 volts, 1.2, even 3 volts. So especially for the lower voltages, if you, let's say, use an LDO and supply it directly, then you lose a lot of power, because an LDO, as you know, is not doing it very efficiently. So what customers, or let's say chip vendors or semicon vendors, typically design is like they have multiple bucks. So DC-DC converter, which efficiently converts the battery voltage to these lower voltages to power things like GPS, sensors, or let's say external memories and display interfaces, etc. For the higher voltages, the 3 volt, you don't necessarily have to use the buck converter, because you are not losing that much power wise. So you also see that there are multiple LDOs that are used in the wearable design while powering these components. And also when it comes to, let's say, heart rate monitoring, you also need to have higher voltages to power the green LEDs, and you have also a boost converter. What I have seen trending in the industry these days is like, instead of having multiple buck converters, because for each buck converters you need to have a inductor connected to it, and then that is basically driving your system cost. So what designers typically do nowadays is like, instead of having multiple ones, we have a single input, which is the input coming from the battery or the VSys from the charger block. And then you have multiple outputs. Having a SIMO design reduces your efficiency compared to a single buck, but I think it's a good trade-off, because you don't reduce the efficiency so much. And the advantage part is like, you just need to have one inductor, so one passive instead of multiple passives and caps around it, thus driving out the system cost. Also, what I have seen as a trend here is like, in some of the products, you see that these are implemented by discrete components. So let's say for each component, you will have a separate buck, a separate boost, LDOs, a separate charger. But this is not a very effective way when it comes to cost. So what are more popular these days is a standalone PMIC, which basically integrates all these components and are quite popular when it comes to more complex watches. But also you can go a step further, where you can incorporate all the power management aspect in the main MCU. And also the connective, and in most of the cases, these MCU also have the BLE connectivity. So especially in the band kind of products where cost is extremely important, you see that the power management, the processing, and also the connectivity, everything is integrated. And I'll show you a product which basically incorporates such a technique. Coming to our third design challenge, which is low power sensing and processing. In this slide, I have basically shown how the data flows, starting with sensing, so sensor data communication and management. So collecting the data from the sensors, it is typically implemented inside the main MCU, or in more complex products, it is realized as a coprocessor. And once you have collected the sensor data, you need to crunch those data through the most complex applications and algorithms. So again, what kind of processors are popular in this space? So in the band space, typically ARM Cortex M series are quite popular in the bands, but when it comes to, let's say, watches and smart watches, I think when launching these products, all the vendors like Apple and Samsung takes quite pride in having a dedicated application processors to do the processing in these complex products, and these are quite state-of-the-art designs in extremely low tech nodes like 7 nanometers, 9 nanometers, and things like that. And the last step of the data flow is, once you have collected the data from the sensor, processed it, then you need to basically send it to the smartphone. So as I mentioned, for the connectivity aspect, low power is also quite important. And the Bluetooth Low Energy is a perfect fit when it comes to data. But also, I think in CES last year, I was there. The Bluetooth SIG also launched LE Audio, which is a new standard for audio apart from the Bluetooth Classic, which they are supporting. And I'll show you what are the advantages of LE Audio. And I think in the coming 4 to 5 years, you see that the latest smartphones are already adopting the LE Audio. And over the course of 4 to 5 years, you will see a migration of audio from Bluetooth Classic to LE Audio. And I think there's also in more expensive and complex products, you also have Wi-Fi connectivity to enable use cases like downloads of music, or even things like firmware updates, because these are quite big chunk of data. And if you try to do it wirelessly over Bluetooth, then it takes a lot of time. So Wi-Fi is the de facto standard over here. You can also do these downloads over USB, but it's not a very good user experience to connect a wire to download, for example, some music files from your smartphones. So focusing more on, let's say, sensing and processing, how does it work? So there are 3 flavors of it that I have seen. I think in the low end products, what you see is, like, as I mentioned, everything is integrated in one single chip solution. And there is, apart from the main core, which is most of the cases, the Cortex M series, the M33 or the M4 with a floating point, you also have a sensor node controller. And this is typically realized by a tiny instruction set, which controls the different interfaces like SPI, UART, I2C, communicating with the sensor, and it collects sensors data. So what is the advantage of this kind of architecture? What you basically do is, like, when the SNC, which is much lighter compared to the main core, when it is interacting with the sensor, you can switch off the main core when the SNC is collecting data, so that you don't burn the power that the main core is dissipating. If the main core was doing the same thing, then you will burn much more power, and this will result in basically a much lower product lifetime. So this is one flavor of it. but also what you see is like in the same flavor, what happens is like the SNC also in some cases has a small code, be it like a 80, it can also be as simple as a 8051 kind of instruction set, or let's say a Cortex M0, so that it adds some processing element to the sensor node controller. So if you want to do simple processing tasks, for example, just let me give you an example of in the band and watch use cases. Every time a user basically takes out his hand to see the time or interact with the watch, then the accelerometer or the gyro sensor is activated. You need to collect data, and you need to run a small algorithm to see whether the user is raising his wrist to interact with the wearable. This is not a very complex algorithm, like let's say heart rate monitoring, or something that you need to do with the display, that you need the main core or even the GPU. So this can be done by the SNC, which has some processing capabilities. So again, you can switch off the main core or the GPU while you are doing this, and in this way you can optimize a lot of average current, and thus product lifetime as well. And in more complex products, typically, as I mentioned, you have a main application processor, which in turn is quite complex. So typically you see that there is a complete different SoC, complete separate SoC, which is implementing the functionality as I explained in these two flavors. It's typically a sensor hub, and it assists the main processor and also drives the power consumption and elongates the battery lifetime as well. Focusing a bit now on connectivity, I have mentioned many times that BLE is the de facto standard when it comes to any IoT product, I must say, which needs to interact with the smartphone. Why it is so popular? I think the most important reason is like because all smartphones these days have BLE connectivity. So it becomes very important, very easy for any product to send data to the smartphone, and the smartphone can basically act as a gateway to upload data as needed to the cloud or do some processing locally as needed. So this is, I think, the most important reason why BLE is popular. But apart from that, I think the protocol is also optimized for ultra low power. The whole concept of designing the protocol was so that you can sustain a coin cell kind of batteries rather than huge capacity batteries. And in this way, in this low power way, you also reduce the cost and size of end product. So even be it a band or be it a watch for data communication, even smartwatches for data communication, BLE is a de facto standard that is used. And talking a bit about LE audio as well, which was launched by the SIG last year. I think it has quite some nice capabilities. A few to highlight is the codec that they have, basically the audio codec that they have adopted, the LC3, can do the compressing in a very nice, in a low power fashion without compromising the quality. So this helps quite a bit. In the traditional Bluetooth Classic, the codec that was used was SBC, and that is not so power efficient compared to LC3. I think talking about two unique things that they have also brought in the LE audio is multi-stream. So talking about again the true wireless stereo, you need to stream music in a synchronized way to both the left and the right channel. So both to the left earbud and also to the right earbud. And in the Bluetooth Classic, this is extremely difficult to synchronize. So you might have seen like many companies have their own patented and proprietary way to do it. Some of the companies, what they do is they basically sense in one of the years and then basically send data from one ear to the other earbud and then synchronize it. But be it any way you adopt, it's very proprietary, I must say. It's not a universal solution and it varies from vendor to vendor. And in most of the cases, it's not very power efficient as well. So with the LE audio, they have a isochronous way of streaming where they basically stream data in a very synchronized way to both the left and the right earbud. And lastly, I would like to also mention, like, they have the broadcast feature. So very interestingly, with the source can broadcast, and let's say multiple slaves, so multiple earbuds can listen to the same set of audio data. So it enables very unique use cases. So let's say if you have a TV or a wearable product as well, then multiple users can basically plug in their headset and can listen to the same audio data. Or even, let's say, announcement system and things like that. You can, in a very personalized way, reach to multiple users instead of connecting to one user and having point-to-point connection. So this is also getting very popular, and I think, as I mentioned, over the course of 4 to 5 years, as more and more phones will adopt this protocol, this will become the universal standard in the coming days. So given that we have talked about most of it, let's look at some of the products that we have. So if you go to iFixit, I think they do some nice tear downs of popular products. So if you look at Samsung Galaxy Watch, it has a bunch of ICs that make this product. You can see that it's such a complex system because you have to pack so many things in such a form factor. But let's see how they have incorporated some of the things that I have just explained in my previous slides. So they have a main application processor, which is the Samsung Exynos, which is quite a high-end and a very nice processing element. But what they have done is they have packed the PMIC element, which basically powers different components and the processor itself in the same package, taking into account different power dissipation. And I think putting PMIC and the processor plus the memory in one package is quite common when it comes to complex products. It is also the case in mobile phones as well. So you don't see a lot of discrete components over here, but you have integrated PMIC IC, power management IC, catering to the application processor and other components as well. And the other aspect which I want to highlight over here is when you see the block diagram of this watch, you also see that they have a separate coprocessor, which they call it sensor hub. This sensor hub also has the possibility to support GPS connectivity. So you see that those kind of techniques are being adopted and are present in the products. And if you will open similar products, then you will also see these kind of techniques being adopted. Let's look at the other end of the spectrum, which is a band. So this I have from the FCC website. This is a snapshot of a Samsung first generation Galaxy Fit band. And this is basically powered by our Dialog solution, the 69X. And I was personally involved in this project. So you see that there is one single SoC, the 697, which is this one, the bottom one in the product, which is taking care of everything. So it's quite a complex SoC, but I'll not go into every detail of it. But some of the details I want to highlight is, you see all the power management is integrated inside the chip. So be it the SIMO DC-DC, be it the LDOs, be it the charger, all the power management things are integrated inside the chip. But also you see that there are multiple cores inside the chip. The M33 is the main core. You also have a sensor node controller, which is interfacing with the different peripherals and collecting data, but also you have a separate core, which is doing the BLE connectivity. And the whole power domain of this chip is architected in such a way that you can independently enable different cores, and then it gives a lot of flexibility to the customer to optimize power consumption to their end product as well. So instead of optimizing each and every element, which you definitely do, you are also thinking more from a system level point of view, and architecting your designs in such a way that you can optimize power from an application point of view as well. So these were the two flavors when it comes to bands and watches, and these are the aspects that you need to take into account while considering or designing for powering and battery management. Let's look at a completely different space, connected patches. It looks very simple, but it has its own challenges associated with it. So for the remaining of my slides, I will look at, I picked just one product, which is the constant glucose monitoring product. And this is again a tear down from iFixit of Abbott. Abbott, I think, is extremely popular company when it comes to constant glucose monitoring, and they ship multi-million units of these sensors every year. So how, as you can see, it is not such a complex design because it's not packed with electronics. So the use case diagram of this is it has a glucose monitoring sensor, and typically you have a dedicated or an ASIC MCU. The USP of this MCU is like it has a very high resolution A to D converter, and typically you have some connectivity, again BLE in this case, to collect either to the reader of the device or directly interface with the smartphone. So what are the power management challenges associated with such a use case? I think the battery itself is the most challenging aspect, be it the output voltage, because you see that the voltage of the typical form factor batteries are 1.5 volts, and the components that you need to power are much higher. So the output voltage is one aspect, but the most important aspect is the series resistance. In order to pack so much of capacity in such a small space, what typically happens is the internal resistance of the battery becomes very high, and you need to focus a lot on how you cater this because it will result in a very short product lifetime if you don't focus on this aspect. The other thing popular with such kind of patches, but in general medical devices, is the shelf life, or what we call in the semicon world is shipping mode. So these devices stay for a long time without the user using it, probably in the fridge of the user or in some places. And you need to make sure that you are not drawing a lot of current from the battery, because if you leak a lot of current, then the battery capacity will be over, and then the user will not be able to use this product. And the last is the product lifetime, how you could be low power, be it especially connectivity wise, I'll focus on, because that is the main power consuming element of this use case, so that you can enhance the product lifetime of these patches. So let's look at the batteries itself. So I have taken some snapshots from some battery data sheet. These are basically some kind of rechargeable batteries or some kind of super caps or silver oxide batteries. One thing to focus here is as I mentioned, the internal impedance. So So you see that the capacity of the batteries are quite less, but together with the low capacity, you also have extremely high impedance, and with temperature, this becomes much worse. So I was associated with one of the designs where we were basically using a super capacitor and some kind of charging element to charge the capacitor, and it was just a simple button that basically the SoC needs to detect the button and basically send the button press to the smartphone for different as a simple RCU. But the whole project revolved around only catering the internal impedance, because you wanted to achieve with a single charge, let's say 30 minutes to 1 hour of lifetime. And bulk of the design challenge to make it a product was how to tackle this internal impedance. And I think the similar situation is with the printed batteries as well. These are quite thin printed batteries. One example I've taken is from Imprint Energy. So one cell is typically 1.5 volts, and again you see that internal resistance is quite high compared to a normal battery where you will expect, let's say, sub ohm when it comes to internal resistance. So so first let's focus on the output voltage. I think it's a very easy way to tackle the output voltage. If the battery is outputting 1.5 volts and let's say if your sensor needs a higher voltage, typically 1.8 or 3 volt, or your connectivity or the MCU needs again higher voltage, then you can place a boost converter. In most of the cases, the boost converter is integrated inside the connectivity chip itself, or you can have a discrete component as well. So that is tackling the output voltage. But more importantly, what happens when you have high internal impedance? So when you have high internal impedance, this graph shows a discharge profile of a battery of such a battery. And there are instances when, let's say, when you will switch on the ASIC or the connectivity chip, then there'll be an inrush current charging all the capacitors. Or let's say when you are doing a transmit or a receive event, then the radio will draw quite some peak current. And let's say if you are not doing anything about it, what happens is like there'll be a IR drop, a resistive drop across the internal impedance. So as you see that the higher the resistance and higher the peak current, you will have a bigger drop as shown in the figure here as well. And let's say if you go beyond the cutoff of the battery, or let's say the minimum voltage that is required by the booster to boost the voltage, then what you will see is basically the system will end itself much faster. So for a 400 milliohm, let's say a higher internal impedance, your cutoff for the battery is much faster compared to a lower internal impedance. So why does it matter? It matters because the faster you reach the cutoff, the lower your product lifetime will be. So how do you tackle such kind of challenges? One way to tackle is like you can place a lot of capacitance just outside the battery. And as you know, the inherent property of a capacitor is to maintain the voltage across its nodes. So that helps, but putting such large capacitors is not economically efficient. So it not only increases the BOM cost, but such form factor devices, these capacitors become very big and are not the most exotic or the best solution. So what typically people do is like while designing the booster, they make sure is the current that you draw from the battery is in such a way that you limit it to certain amount so that you don't have such a big voltage drop. So that is also what, just to give an example, what we have done in one of our SoCs, which is the 531. So this is basically a graph where basically the main SoC is sleeping most of the time, and then it wakes up to have an inrush current. then you do some processing, and then you have a few radio events transmit and receive. So what the booster, which is integrated inside the chip, what it does, it has a property to limit the amount of current that you can draw from the battery. So in this way, you are also controlling the voltage drop and thus enhancing the cutoff time and also the product lifetime. So this is when it comes to batteries. So let's focus on the second challenge, which is long product shelf life. So this is just again the same Abbott CGM sensor with the reader. And if you look at the FDA site, what it states is like this sensor has a storage life of as long as 9 months, whereas the product lifetime is just 10 to 14 days. So you can see here is like the shelf life of such medical products are extremely long. And these are in most of the cases also stored at quite some low temperature. So low temperature is beneficial in some way, but also not beneficial in some ways, because in low temperatures, the capacity of the battery also decreases quite a bit. So the problem statement here is to sustain a long shelf life when the device is powered by a low capacity battery and the product is typically stored in low temperature. And what are the solution, or the how the industry tackles is like you typically power off all sensors and set the main MCU in hibernation mode. And the hibernation mode, you design it in such a way that you are only consuming a few hundred nanoamps. And in this state, you also need to design the chip in such a way that you need to have a wake up possibility. Let's say if there's a trigger in the GPIO or the sensor detects something, then it will wake up the main MCU to do the reading, the processing, and basically sending the information over there. But designing such MCUs with low hibernation current, especially if you are designing in lower tech nodes, is not very easy. Because in lower tech nodes, you have very highly leaking standard cells. So there's a lot of challenge. You need to use specific libraries when it comes to designing only certain parts of the wake up element of your chip. And also you need to define your whole power up and wake up sequence in such a way that minimal components are powered in this hibernation or sleep mode. So this is how you make sure that you have your product, especially in the medical space, have a longer product shelf lifetime. Lastly, the product lifetime itself, again, the same example of the same product. You see that the lifetime of this patch is up to 14 days. And how do you make sure to achieve this lifetime of 14 days from a silver oxide batteries, which is typically, let's say, less than 10 milliamp hour. So as I mentioned below, before, the current profile of such a system is like the system is sleeping most of the time, and let's say if there is a sensor event, or let's say after a fixed amount of time, the MCU will poll the sensor, collect some sensor data, do some processing, and basically advertise the data over there. Advertise is basically a methodology in the BLE protocol where you broadcast the data over there, and any device which is basically in the same channel space can listen to the data and collect the data. So important thing to note here is like when you zoom into the state when the SoC is awake, then you see that there's a lot of power consumption being consumed, being the main core that is drawing the current, or the transmit or the receive events that are drawing the current, the radio which is drawing the current. So these are typically, if you see, it's already the average current just in the advertisement space will be at least a milliamp hour. And if you draw such a current from, let's say, a 10 milliamp battery, 10 milliamp hour battery, then your product will last only 10 hours. So what is the trick behind it is like you basically put your application in as long as possible in the sleep state, of course, without compromising the performance or the connectivity. And then you design the your main MCU or the SOC in such a way that the sleep current, which is a very critical parameter, which drives down the average current, is as low as possible. So these are some of the power management aspects that you need to take into account when it comes to medical patches as well. So this draws me to the conclusion slide, which is the message is actually very simple. Be it a complex product like a watch or a band or a simple product like a patch, which is made up of a few electronic components. When it comes to power management, the challenge is the same. And as a designer, you need to focus on always the end user. What will be it to the end user, how they will experience it, and that is the key to making a successful product based on my experience and in my opinion. So that was it from my side. Thanks a lot for attending my talk, and I hope you learned a lot from it from a power management point of view, and you have a similar mindset when you will be tackling your design, tackling the power management design challenges when you are designing your products. Thank you.